looking at phrases that look like this right here, like that right there. So just look at that, just that one right there. This is one of the rules we're going to get to work with, which is if you're integrating from a to c. So that says the integral of f of x from a to c. You could also say the integral from a to c of f of x dx. You could say it that way. You can. What does this rule effectively tell you you're able to? What does this rule tell you you're able to do? What can you do with this rule? Yeah.
You can break down an integral into parts.
Yeah. So you can break an integral into two pieces. You can break it into two pieces. So you'll notice that what?
Is it a max of two pieces? Or
Nah. So if you can do this, if this is true, could you break a to b into two pieces? So you could break it into as many as you want. Absolutely. The key thing to realize is this: you're starting at a, right? And where does it have to end? At the same place. It has to end at c. Now, do you see b? Hold on a sec. 3. Do you see b anywhere on the left side of the equation? There is. That's a key thing to realize. Is there b anywhere in there?
Well, there is, but we don't see it.
Well, no. Is b listed anywhere in there, right? It's not. So what value could b be? Anything. That's really important here. So you might assume that b has to live where? Where might you assume b has to live? In between a and c. Does it have to live between a and c? It does not. B does not have to live between a and c. You will frequently break it apart into two pieces, or you can go backwards, by the way. You could glue things together, right? But the point is, does b have to be between a and c? It does not. That's really, really important. B does not have to be between a and c. It does not have to live in the set a to c. It does not. It can be outside. There are certain times when it's to your advantage to not pick something between a and c. What does this tell us right here? What does this rule tell us for b? What does this rule tell us we're able to do? What is this called? Like we have a word you've used many times before. You're taking this c and you're doing this. What's that called? Yeah. In this case, by the way, in this case, c is a constant. A, b, and c are all constants. And the c is a constant. It's c times the function f of x. So if you have a constant times the function f of x, you can do the integral first and then multiply what you get times the constant. This just tells you can factor out constants from an integral. It has to be a constant times the entire function, though. So this is just, you can factor, yay. What about this one right here? What does this say? Let's take a look. Everybody, even though this is what is written up here is totally mathematically proper, I like putting big parentheses around. That's just you're taking the integral of that. What does this tell you you can do? What does this tell you you can do, David?
Separate it?
Yes, exactly. The integral of the sum of two functions or the subtraction of two functions can be done separately. You can do each one individually. Will that help you at some points? Absolutely. Like sometimes you're going to be working on an integral and f is going to be really, really straightforward, but g is going to be a pain in the butt, right? So what do you do first? Well, do the easy part. Do the integration for f. And then you might have to learn something about how to attack the second part. But you can do them in pieces. You can do them in pieces. You can do them in pieces. Okay, so let's take a look at, so what does f of x look like? Oh, let's not actually use that. So let's say, what does y equals x look like? Well, that equals this, right? What about y equals x squared? There's y equals x squared, right? Correct? So where is the area between them?
3 and 5.
This one goes up like this and this keeps going, right?
Yeah.
Goes like this, right? Goes between them.
So,
Oh wait, from what to what?
from 3 to 5.
From 3 to 5. So did I graph enough of this? Did I graph enough of this? Really?
I can't tell what this goes.
Yeah, well you can figure it out. This is the intersection point, right? Where do these two graphs intersect? What's the x value right there, where they intersect?
2.
Where does x squared equal x, everybody?
1.
Yes. Where does x squared equal x? That equals that x equals 1. So I ask you again, have I graphed enough of this graph? No, I have not. So you're going to actually have to graph the whole thing. So y equals x squared goes like this, right? And I'm not doing this very to scale at all, but here's y equals x right here. Does everybody see that right there? 3 to 5 is going to be out here, correct?
So it's g of x minus f of x.
So which one is it going to be? It's going to be what's the upper function?
G of x.
That's the upper function in this case, right? And what's the lower function? Well, the other one, right? So what's the integral expression going to be?
G of x minus f.
So the integral from what to what?
3 to 5.
The integral from 3 to 5 of
G of x minus f.
g of x minus f of x dx. You could absolutely write it like that because does it say somewhere else on your page what f of x and g of x equal? Absolutely. Absolutely. Yes, Chris.
So, what were you saying about like the upper and lower? Is that just...
The upper function, x squared is g of x.
Yeah.
So it is above. So in this region right here, here's 3 to 5, like 3 to 5, this is a terrible graph. I'm doing a terrible job of graphing this today. So here's x squared like this.
Yeah.
Y equals x squared. And then y equals x is like right here. 3 to 5, let's say, is right from there to there. So the region we're trying to find is right here, this yellow region right here, from 3 to 5. So you're integrating from 3 to 5 because that's what it's telling you, you're going from 3 to 5, right? What's the upper function? That's g of x right there. And what's the lower function? Well, that's f of x right there. So you're subtracting them. Because what are you functionally doing, everybody? You're finding this whole thing right here, and then you're subtracting out the bottom part.
What I was going to ask.
Yeah, go ahead.
Can you find...
When x is greater than 1, g is greater.
Yeah.
So you have to do g of x minus f of x. So let's actually look at this for example. What was g of x? That was x squared, right? It was 3 to 5 of what? So x squared minus what? Dx. Now, what did that rule tell you you could do? One of those rules above told you you could do something to that. What can you do? Yeah, Noah?
Separate it.
Yeah, so you get the integral from 3 to 5 of
X squared.
dx. You have to write the dx in there. Minus the integral from...
3 to 5 x dx.
And this is one you guys can do by hand. What is the integral of x squared? You know how to do... We did this a little while ago.
X cubed.
Careful, it's going to be x cubed, right?
X cubed.
But what do you put out front? What do you put out front?
N plus 1.
Yeah, but careful, not n plus 1 is there. The derivative of what is x squared? The derivative of what is x squared?
1/2.
Careful. Someone say the whole thing for me. The derivative of what is x squared?
1/3 x cubed.
1/3 x cubed. From 3 to 5 minus, what's the derivative of what is x?
1/2 x squared.
1/2 x squared from
3 to 5.
3 to 5. And the way you do that would be 1/3 5 cubed minus 1/3 what? 3 cubed minus what?
1/2 5 squared.
5 squared minus
1/2.
3 squared. Right, exactly. So what can you do? Oh, it's going to be what? 125 over 3 minus 27 over 3, which is 9. You know, I'm just keeping the thirds in there. Minus what? 25 over 2 minus... I'm evaluating. Are you guys with me so far?
Yeah.
You with me? I'm just doing some fraction work here. And I'm not why am I not simplifying that right there?
Because you can just subtract it.
Now I can subtract it, right? What's that going to be? How many?
98 over 3.
98 over 3 minus what?
16 over 2.
16 over 2, which is 98 over 3 minus 8, right? Change it into thirds. How many thirds are in 8?
24.
So 98 over 3 minus what?
24 over 3.
So what's that going to be?
74 over 3.
Yeah, and that would be your final answer. So that would be the exact answer right there. You just did an exact integral right there. You did an exact integral. How are you feeling about what we just did there? Except for my really terrible sketches. I'm sorry. I apologize. David and then Noah. Yes?
Where did the antiderivatives come in?
Where did the antiderivatives come in?
Yeah.
You mean, what do you mean exactly?
Like, I just like didn't see why you put them in.
Because of that symbol right there, the area, the integral symbol right there.
Alright.
So how do you remember what we've done before? The integral from a to b of f of x dx is equal to what? The integral of b minus the integral evaluated at a. So what did we have to do? This was the function, right?
Yeah.
So we did it in 2 pieces. We did it in 2 pieces. What is the integral of x squared? I should really not use that highlighter with red. I'm sorry.
Yeah,
What is the integral? 1/3 x cubed. The integral is right there, right? And what's the integral of x? 1/2 x squared. That's where it comes from. Okay?
I didn't have a question. I was doing the number thing.
Then, oh, you were telling me.
That's where
Good.
we're going.
No, that's fine. We can do that. People, how are people feeling about what you see right here? How are you feeling about what you're seeing right here?
Can you just
Go ahead, don't apologize.
Just remind us of the
Yeah?
to get the x derivative. I know it's
To get the what? The
antiderivative.
Yeah, so you know how to do one type of antiderivative right now. So if you have, let's do the super general form of it, okay? That's a great question to ask, Chris. So let's say I had ax to the n power.
Yeah.
That changed, that's fun. Ax to the n. What's the integral of that going to be? X to the what power? Just do it logically. What power does it have to be? You're going up. N plus 1, right? But that a is still there, so it's going to be a over what? N plus 1. Because when you take the derivative of this, what happens when you take the derivative of that? You drop the n plus 1 to the front, and what does it cancel with? The n plus 1 in the denominator. And then what happens to the power when you take the derivative? It goes down by 1. The derivative of a over n plus 1 x to the n plus 1, what's the derivative of it? Ax to the n. That's where it comes. So this is the one type of integral you know how to do. Are there many, many others? Yes, this is the first one because there are many functions that don't fall in this pattern. So just to be really clear about this, for example, like 2 to the x, do you have any idea what the integral of that is right now? Can you tell me the wrong thing? I very rarely ask this because I do not like reinforcing wrong things. Can you tell me what this definitely doesn't equal? David, yeah.
1 over x, 2x plus 1.
Exactly, something like that. No, not even close, okay? Don't do that. Not good. Not good. Logs get involved in that. It's really not that bad, but you just have to keep it separate. It's kind of like when you work with logs in general. Some people think working with logs is really challenging. It's actually really straightforward if you don't make stuff up, right? The problem is it's really easy to make stuff up when you're working with logs. You're like, this is clearly a rule. Like, no, it's not. Like, no. We were through